Right, welcome everybody to this special lunchtime Geotalk. It's extra special because we are, as you can see, live from the Geoscience building and there are actual people in the room. And not only that, there is also a live presenter, which hasn't happened for about 2 years. So that's really exciting. And for those of you that are watching online, I'm going to entice you back here next week because we have drinks and, not today chips, but we have drinks sponsored by John Hancock's and CCIC Group. So please do come along in future if you feel like you need some in-person science. This week, we welcome Andrea Giuliani, who is joining us all the way from Switzerland. He's here for a visit to South Africa and kindly offered to give a talk this afternoon. So thank you, Andrea, for that. Andrea, as you will tell, hails from Italy, where he did his undergrad and his MSc degree, and then went to Australia to get his PhD from the University of Melbourne, and has had several prestigious postdocs since then, and is now working at ETH in Zurich as a Swiss fellow. So Andrea, thank you so much for joining us, and we'll get your talk loaded up. Stop that share and right, I think you're ready to go, Andrea. Okay. So over to you.
Yeah. All right. Thanks for the introduction, Grant. Hello, everyone, both in the room and online. It's really imposing all these lights in the darkness in the room, but it's fine. I mean, I just need to get used to it.
You want to minimize that video chat?
Yeah. All right. So, well, I guess the title of the talk is focused on the global carbon cycle, but actually the talk, and this is why the title is a little bit different, starts with a broad introduction on Kimballites, and as a mean essentially then to drive you into what Kimballites can reveal us about the global carbon cycle. And hence, okay. So, I mean, being in South Africa, introducing Kimballites is quite straightforward because for most of you, these rocks are pretty much in your backyard. But anyway, the reason why most people are interested in Kimballites are fundamentally for two reasons. First of all, these are the major host of diamond deposits, and I can tell you that's why many people might think that carbon is just a very well marketed piece of carbon from which De Beers managed to make a lot of money. Actually, when you stand in front of big bunches of diamonds, I mean, things get really excited. And this is myself and Jock Robbie in the diamond processing plants of Kimberlite, where we're staring at those trays full of diamonds. And this is myself and John Woodhead looking at the personal collection of John Gurney when John was still with us. But the other reason why Kimballites can be quite interesting is because these are the deepest magmas that we find on the Earth's surface, and therefore they can provide us a wealth of information about the composition and evolution of the deep Earth. And this is the way we're going to use them today. So in this map of the world, this topographic map of the world, in the salmon-colored fields are the so-called continental shields, so cratons and pericratonic areas, and Kimballites are reported as red diamonds, and when they are being mined for diamonds as yellow diamonds. What is quite clear is that Kimballites essentially only occur in continental shields, and then been found in pretty much every continental shields with a couple of exceptions. And the chart on here is that you can see the distribution, the temporal distribution of Kimballites through time. It's clear that the vast majority of them are essentially Mesozoic, or if you prefer, Phanerozoic. We have a few occurrences dating back into the Proterozoic, as far as back as 2.1 billion years, with a couple of older reports, of which I'm personally not that convinced of after having had a look at this oldest Kimbalite here, which is from Gabon. But anyway, anyhow, definitely they occur since at least 2.1 billion years ago. One fundamental misconception of people that don't know Kimballites well enough is that they are typically diamondifers. They're actually not. Even when they are, diamonds only occur at the sub-part per million level. In other words, if you grab, say, a couple of kilograms of Kimbalite rocks, it's extremely unlikely you're going to find even just a tiny diamonds in it. Beyond that, Kimballites are very complex and hybrid rocks. I say hybrid because they consist of a mixture of crustal fragments, such as this white and red stuff down here, as well as mantle fragments, diamonds, of course, but various megacrystal or various xenoliths, so eclogites, peridotites, so rocks that actually come from the mantle, which are mixed into a matrix mostly, but not entirely, of magmatic origin. And these samples, these are photos that I took within the Karowe mine in Botswana. Fundamentally, the two main constituents of fresh Kimbalite rocks are olivine, the mineral that here you can see colorless in these thin sections of the grizzly Kimbalite from Canada, and carbonate, which here forms the matrix of these breccia-like Kimbalites from Leicester. There are also other phases, of course. So usually there is a fair amount of serpentine in most, but not all Kimberlites. Some people consider magmatic. Other people, including me, consider to be more likely to be a hydrothermal phase. But anyway, that's not the focus of the talk today. So these I want to make it as a statement because there's still a little bit of literature out there that states the opposite. Kimballites derive from the convective mantle, and we have quite a few quite strong pieces of evidence backing up this statement. First of all, Kimballites host some Kimballites, not all of them, host the so-called superdeep diamonds. So diamonds that contain inclusions of phases such as ringwoodite or potentially calcium silica perovskite, which puts the formation of these diamonds within the mantle transition zones or even the uppermost lower mantle. Of course, this doesn't necessarily mean that the Kimballites are sourced at these depths. And here I summarize 4 different models of Kimbalite formation. Either Kimballites can form directly in the lower mantle, even though this has some potential complications for essentially moving this low debris melts all the way from the lower mantle to the surface, can form in the transition zones, or more likely form in the upper asthenosphere, either due to impingement of deep-seated mantle plumes or by simple convective processes. In either way, to transport diamonds that were either in the transition zones or by mantle convection transported to the lithosphere-asthenosphere boundary, we need partial melting to be at least as deep as the asthenosphere. Change automatically. Then we have a bunch of geochemical lines of evidence. First of all, let's start with the chart on the right-hand side. These are trace element spider diagrams for various Kimballites worldwide. As you can see, they have remarkably similar trace element patterns, which point to broadly similar, but not identical, of course, mantle sources. On the right-hand side, on the left-hand side, there is something a little bit more tricky, perhaps, to understand. This is a plot of average magnesium number of olivine versus average magnesium number of xenocrystic olivine in Kimballites worldwide. As you can see, the 2 parameters are tightly correlated. And the only way to explain that is if the source, the primary melt composition, and therefore the source of Kimballites globally is broadly similar, and you assimilate either refractory and therefore magnesium-rich lithospheric material or more geochemically enriched and therefore lower magnesium number enriched material. By assimilating depleted or enriched material, we just move along this regression. The important point here is that Kimballites must derive from broadly similar mantle sources in terms of major elements and also in terms of trace elements. Then we have pieces of evidence from geophysics, geodynamics, and geochronology. So this is something that Phanerozoic proposed some 10 years ago. The chart on the left and on the left hand here. So if you reconstruct the position of Kimballites back at the time of their eruption, most of them overlap the current position of the so-called LLSBPs, so large low shear velocity provinces. These are mega structures just above the core mantle boundary where seismic velocity are lower than the average mantle, and which are considered to be the regions of origin of mantle plumes. In other words, what Thorsvik and his colleagues propose is that the majority of Kimballites are 80% for the Phanerozoic are related to mantle plumes that are sourced just above the core mantle boundary from these so-called LLSVPs. This might sound a little bit esoteric, but we have perhaps even more solid evidence from geochronology and geodynamic reconstructions, for example, here on the right-hand side. This is a nice chart from Larry Heeman from 2009 in Elements. Actually, the original idea is from Larry Heeman and Bruce Kjaersgaard in 2000, where they dated Kimballites along in northeastern North America, and they found an age progressive track, which then continues into the North Atlantic, where it generates the New England seamounts, including some islands above the sea level. What they suggested is that the Kimballites along the Great Metro Hotspot track in the New England seamounts are related to the same mantle plume on top of which the North American plate was just trailing. In other words, Kimballites can potentially be linked based on these two pieces of evidence to hotspot tracks ultimately sourced in the lower mantle. A link between Kimballites and ocean island basalts, most of which are indeed related to deep mantle plumes, can also be made based using isotope geochemistry. This is a summary chart from the nice review paper of Sebastian Tappe from in 2018 and his colleagues. Neodymium isotopes versus hafnium isotopes. The gray field are ocean island basalts. The Kimballites, Phanerozoic in blue and Proterozoic in red, nicely overlap most of the ocean island basalt field, excluding this more depleted field, which are the OIBs, the ocean island basalts related to mid-oceanic ridges, where there is, of course, more depleted material being tapped. Recently, we moved potentially a step forward, and we analyzed many more Kimballites globally. And what we found is that essentially the vast majority of Kimballites plots along just scattered along a regression, both in terms of neodymium isotopes versus time and hafnium isotopes versus time. And this to occur requires that Kimballites have been sampling potentially the same source for over 2 billion years. If that is the case, then it's likely that this source has been more or less isolated, at least up to a few 100 million years ago, where we start to have a lot more scatter, and therefore this source has to be very ancient, at least 2.5 billion years. Recently, I tried to move even a step forward, and essentially together with Matt Jackson, Angus and Hayden, we reviewed all the existing data for Kimballites and related rock, including strontium, neodymium, and hafnium isotopes, and we look at things more closely, also using petrological constraints. Anyhow, here again, there is time. Here there are neodymium isotopes, and here there are all the Kimballites from 2.1 billion years to present day, excluding some of the most enriched ones over here. What we realize is that if you select the most depleted Kimballites, so the one with the highest neodymium isotope decomposition and every single time, then essentially all these points plot along a very robust regression, which we define as the depleted Kimballite source. This is an N member that essentially we find in all the Kimballites. This depleted Kimballite source is intermediate between the depleted mantle, that is sampled by mid-ocean ridge basalts, and the bulk silicate earth, which is derived from chondritic chondrites, so from meteorites. That's fair enough, but what is interesting is that if we look at this regression, if we extrapolate this regression back to the age of the Earth, then we get an initial value for the depleted Kimbalite source here called Prima that is indistinguishable from Cher. Of course, this is quite a bold statement to do because we are extrapolating data from 2 billion years to 4.5 billion years. But if the extrapolation is valid, then it would seem like this component in Kimballites derive from early depletion of a chondritic Earth. Okay, so the Earth accreted and they went partial melting, various partial melting events, potentially, definitely some magma ocean stages, and the depleted residue is what Kimballites have been sampled throughout the second half of the Earth history. The question, of course, is what is this depleted component? And to answer that question, we compared it with the composition of ocean basalts today, hafnium isotopes versus neodymium isotopes on the left-hand side, strontium versus neodymium isotopes on the right-hand side. It's been well known for over 30 years that ocean basalts from a given island chain have compositions that trend towards a common end member that is called Prima or FOSO. This is generally considered to be a fundamental component in the Earth mantle. And perhaps not as surprisingly, the depleted Kimbalites component that I showed you before perfectly match or is within the range of this Prima prevalent mantle or FOSO focal zone composition. In other words, it's apparent that Kimballites have been sampling this Prima component for over 2 billion years. And that potentially implies that Prima is not a product of mixing between depleted and enriched components, but perhaps it's something that is as ancient as the age of the Earth. Anyway, I don't want to spend too much time on this. I'm happy to chat about this a little bit more later. The last slide before I move on to the carbon cycle is this very recent work that just came out a couple of months ago. So now Nakanishi and Rich Worker in the lab, they measured a bunch of Kimballites with a sort of Prima composition, as well as a couple of Kimballites with a geochemical enriched composition. And I found that the Prima-like Kimballites have a tungsten 82 anomaly, negative anomaly compared to their laboratory standard, whereas the more enriched Kimballites do not have this anomaly. This anomaly can be only explained in two ways. Either Kimballites have a component that is derived from the core, which has a very negative tungsten 182 composition of about estimated to be around minus 220, or Kimballites essentially tap a domain, a mantle domain that was generated very early in the Earth. Why this? Because tungsten 182 derives from radioactive decay of hafnium 182, and the lifetime of hafnium 182 is just 9 million years. Okay, therefore, any anomaly had to be produced by early Earth differentiation within 60 or so million years of Earth accretion. So either the source is very ancient, or the source is very deep, or both, based on this tungsten isotopic data, which is consistent with the radiogenic isotope data I showed you before. So all this huge incipit, this huge introduction is just to say that Kimballites most likely are very deep melts, potentially as deep as just above the core mantle boundary, in terms of their source. Partial melting may very well occur just below the lithospheric mantle, but what we care of here is really the source. And also what we care, at least for this talk, is what Kimballites could tell us about the carbon cycle and how we can use them to track that. So this is a slide that I borrowed from the Deep Carbon Observatory, which provides a very nice summary view of the global carbon cycle. Each round, each circle represents a different reservoir, and the larger is the reservoir, the larger is the size of the carbon reservoir. So for the core is pretty large. The upper and lower mantle are comparable, if not bigger than the core. Much less carbon is in the exosphere, so atmosphere, ocean, and terrestrial biosphere. The blue arrows indicate the movement of carbon between this reservoir. So in terms of global carbon cycling, the major sink, of course, is subduction, and sink in terms of mantle sink. And the major outputs is from volcanism, either due to plumes, to mid-oceanic ridges, to arc volcanism, to rift. Now, of course, there are also other fluxes, for example, metamorphism, especially in convergent margins or elsewhere, and so on. In any case, the point that I want to make here is that we have quite a robust understanding of the global carbon cycle today, including values, well-constrained values for many of these fluxes, not all of them. What is far less well-constrained, I did something funny here, okay. What is less well-constrained is how the deep carbon cycle is changed through time. And because Kimballites provide information for the mantle over the last 2 billion years or so, then that's a way, maybe there is a way we can use them to track variability in the carbon cycle. So a easy way, I guess, to track carbon through the Earth is by using carbon isotopes. And the reason is simple. There are vast differences in carbon isotopic compositions between carbon that we find at surface and carbon in the mantle. At surface, carbon occur in two forms, either carbonates with a delta 13 carbon isotopic composition of around 0. Delta 13 carbon is just essentially a ratio of 13 carbon over 12 carbon compared to a standard, usually seawater, PDB, belemnite. Whereas for organic carbon, this is considered usually to be between -25 and -30. And these are just some values. These are how the reservoirs have changed. The surface reservoirs have changed through time, just to give you an idea of the variability. For the mantle, the value that we usually consider to be representative is -5 ± 1. And this is mostly bracketed by diamonds, peridotic diamonds on here, eclogitic diamonds there, to a lesser extent oceanal and basalts, but also generally carbonatites and kimballites, most of which plots range around this, plot within this interval. For oceanic basalts, many values are actually lowered, and this is attributed to the gassing. CO2 is very is not particularly soluble in basaltic magmas, and therefore most of it is released before basalt emplacement. For eclogitic diamonds, though, you can see that the distribution is quite heavily skewed towards very low values, where heavy values, so values around 0 higher, are rare. Eclogitic diamonds are diamonds that are commonly considered to be, in most parts, connected to deep subduction of crustal material based on the currents, on their inclusions, but also based on oxygen isotopes of their inclusions, sulfur isotopes of their inclusions, and carbon isotopes of the host diamonds. So the interesting observation that I want to make here is that the fact that there are many diamonds with very low carbon isotopic composition that is usually attributed to cycling of organic carbon in the mantle, compared to very few with the carbon isotopic composition consistent with recycling of limestone, implies that recycling of limestone in the mantle of carbonates, surface-derived carbonates in the mantle, is not particularly effective. So subduction zones provide quite a barrier towards subducting oxidized carbons compared to what we see for organic carbon, so reduced carbon. And this is important for the remaining of this talk. But what about Kimballites? Carbon in Kimballites occur as carbonates. And as I told you before, diamonds are extremely rare and are xenocrystic in origin. And the potential issue is that there are different forms, different petrographic forms of carbonates. We have carbonate segregations. Well, actually, let's start with the ground mass. So this is most likely carbonate of magmatic origin, consistent also with trace element data or strontium isotope data, for example. Then we have veins that are most likely to be of secondary hydrothermal origin, so crustal origin. And finally, we have segregation that's origin of which is not always clear. And so you need also to look at things like trace element or strontium isotopes to figure out whether they are magmatic or not. But anyway, for the sake of this talk, we're more interested in the carbon isotopic compositions of these different types of carbonates. So Mongari Castillo Oliveira, a postdoc that worked with me while in Australia a few years back, she did a very meticulous work documenting the petrography, major trace elements, strontium isotopes, and carbon oxygen isotope carbon isotopic compositions of carbonates in several samples. What she found for carbon is that there is quite variability in any given sample. Okay. However, she also found that the bulk composition of the bulk carbon isotopic composition of Kimbalite carbonates usually sticks more or less to the main mode of the distribution. I did something else to make sure that if we measure bulk Kimbalites, we actually obtain a representative carbon isotopic composition of the magma. And I compared the bulk sample delta 13 with the average measured in situ for magmatic carbonates only. Okay, so I didn't consider the calcite veins. I only considered calcite segregations that were pristine magmatic. And then I took an average of these for every sample and I compared it with the bulk rock. So if this is a one-to-one line, and the samples typically just scattered along this one-to-one line. Okay, there are just a couple of exceptions. In other words, the purpose of this exercise was to test whether or not we can just use bulk Kimbalite carbonates to obtain a carbon isotopic composition that are representative of their parental melt, and therefore avoid the complications of having to do a lot of in situ analysis by secondary ion mass spectrometry. And apparently this works. So armed with this knowledge, then myself and a bunch of colleagues moved on and measured something like 200 or so samples of Kimbalites worldwide from 140 localities to complement the existing database. Importantly, we only looked at intrusive Kimbalites. So volcanoclastic, pyroclastic Kimbalites were not included in this compilation. And this is how the data look like. So this is carbon isotopes on the left axis, on the y-axis versus time on the x-axis. So clearly there are two different groups, if you want. So Kimbalites older than roughly 250 million years, all of them are within uncertainty of the mantle range with one exception. Kimberlites younger than 250 million years show a very different distribution where at least 1/3 of the samples are clearly resolved from the mantle range. So this is what I call a perturbation of the source of Kimbalites by isotopically light organic carbon. Now we need to figure out, first of all, what is the source of this organic carbon, and secondly, why we see this perturbation only after 250 million years. So for this reason, I switch back to radiogenic isotopes for a moment. So this is now strontium isotopes versus time, and these are again a bunch of Kimbalites. Strontium isotopes of perovskite, so a ground mass magmatic phase, not bulk rock, just to make sure that there are no problems with contamination. And this is a little explanation chart that indicates that whenever you have a partial melting event, what you extract, so your partial melt, say the crust, has higher rubidium strontium and therefore with time develop more radiogenic strontium 87, strontium 86. What is left behind, so the depleted product has lower rubidium strontium and therefore with time develop a more depleted, so lower 87, 86 ratio, more depleted composition. What we see in Kimbalites is that we see a lot of highly radiogenic strontium isotopic composition only after about 250 million years. And the best way to interpret this, and this is the way we interpret it in this paper, for example, is if substantial recycled crust, subducted crust only occurred in Kimbalites younger than 250 million years. An idea that was first put forward with John Woodhead in the 2019 Nature paper. So it looks like we see something similar in the carbon isotope distribution and strontium, as well as neodymium and hafnium isotope distribution of Kimbalites through time, with a perturbation occurring after 250 million years. If we now compare carbon isotopes with the strontium isotopes, the chart on the left-hand axis, and carbon isotopes versus hafnium isotopes chart on the right-hand axis, indeed, we can find a broad correlation. Of course, the correlation is not particularly great, and this is not something I was personally expecting. We're looking at elements that are concentrated in different minerals. We're looking at very complex rocks that can have crustal material, mantle debris, and so on, that experience some of them hydrothermal alteration and the like. So the fact that we observe a broad correlation is already quite a finding, I believe. And what's interesting is that carbon isotopes become lower with progressively more radiogenic strontium isotope composition. So if you believe what I said before, that this is an indication of enrichment by subducted crustal material in the source of Kimballites, then this also means that this carbon is related to deep cycling of crustal material in the Kimballite source. And the only way for this carbon to become lower is if this subducting material hosts organic carbon with light isotopic composition. The same applies for hafnium isotopes versus carbon. These additional lines and these gray plots are the results of modeling as well as Monte Carlo simulations, just to show that this scenario is indeed feasible. That is, most of the carbon and hafnium isotopic compositions of Kimballites can be explained by mixing a prima-like depleted Kimbalite source with subducted sedimentary material hosting organic carbon. And if you would like to have more details, I'm happy to explain that in more detail. Importantly, these two trends are completely inconsistent with the gassing of CO2. I stress this because I've had a very hard time with reviewers for this paper that were pushing and pushing the button where some of these light carbon isotopic compositions, or actually most of them, were related to CO2 degassing. Perhaps some of them are. I cannot completely discount that, but certainly you would not expect a correlation between strontium and hafnium isotopes, which are not affected by CO2 degassing, and carbon isotopes, if CO2 degassing was the only reason why some Kimballites have lower carbon isotopic composition, and only after 250 million years. So I think probably we have a trigger, recycling of subducted crust, and most likely of sedimentary material in the deep source of Kimballites. Now we need to figure out why we can see this only during the last 250 million years or so. This is again a chart. Something else that popped up there. Anyway, it doesn't matter. This is a chart of time versus carbon isotopes up here, which though is restricted to the last 1 billion year. So the same data as before. Here I have plotted the distribution of Kimballites through time. And here there is a total organic carbon versus in shales. Let's forget about these down here for a moment. So what is interesting is that when we start to see low carbon isotopic composition in Kimballites, that's also when the so-called bloom of Kimballites start. That is at about 250 million years ago. In other words, we see so many more Kimballites during the last 250 million years when many of them start also to have carbon isotopic compositions lower than typical mantle values. For the bloom, the increase of Kimbalite eruptions through time, the frequency of Kimbalite events through time, was previously explained by the onset of cold subduction in the Phanerozoic, because with colder subduction, recycled crustal material is more efficiently transported in the convective mantle. This, however, has a couple of problems. First, the cold subduction now is well constrained to have started at about 850 million years ago, whereas the bloom in Kimballites, it only starts at about 250. So there is a 600 million years gap. And secondly, there is increasing evidence of cold subduction already in the Paleoproterozoic, for example. There is a nice paper just out in Precambrian research that show cold subduction in some Chinese complexes already in the Paleoproterozoic by Kuski and co-workers. So we definitely need something more. Yeah, definitely cold subduction might have played a role, but that's not sufficient. So something else that happened on the Earth at about 540 million years ago is the so-called Cambrian explosion. This is a massive change in marine productivity that is linked to the explosion of multicellular lives for the first time in our planet. And this is why I have this chart down here. These coincide with an increase in organic carbon deposition in the sea bottoms, as indicated by total organic carbon in shales through time. So the idea that I'm trying to push here is that with the Cambrian explosion, we have more organic carbon deposited in marine sediments, and therefore more organic carbon ultimately subducted in the deep earth. Yet you might very well argue that there is still a 300 or so million years gap between when these events start, so the Cambrian explosion, and when we have the Kimberlite bloom, and importantly, this perturbation in the carbon isotopic composition of Kimballites. So to address this apparent dichotomy, we can turn to geodynamic reconstructions. So this is a chart that I borrowed from a recent chapter in the AGO monograph by Strontium. And these charts essentially show that once you take into account the time that subducted slabs take to travel all the way from the surface to the core mantle boundary, that is 150 to 200 million years, plus the time that subducted slab just to travel along the core mantle boundary, which is another 20, 30 at least million years, plus another 20 or so million years that mantle plumes take to travel after sampling some potentially subducted crustal material. The mantle plumes take to travel all the way up from the core mantle boundary to the surface. Well, the overall time that you get is 250 to 300 million years. Perhaps just coincidentally, this is more or less the time gap that we see between the Cambrian explosion and the onset of the Kimbalite bloom and the perturbation in the carbon isotopic composition of Kimballites. So the idea that I'm pushing here is that this fundamental change in the shallow carbon cycle that was obviously triggered by the Cambrian explosion might have had an impact on the deep carbon cycle. In other words, changes in marine productivity and therefore increased export of organic carbon to sea bottom and ultimately subduction might have ultimately modified the carbon budget and isotopic composition of regions of the deep earth, that are sampled by Kimballites. So to conclude, the data show that the Kimballites record a perturbation in their source, both in terms of carbon, strontium, neodymium, and hafnium isotopes. And this is after 250 million years ago. This change, especially for carbon, is potentially linked to fundamental changes in marine productivity and therefore in the shallow carbon cycle. In other words, what I'm proposing here is that there might be a feedback between biogeochemical processes that occur at Earth's surface and mantle processes, and therefore magmatic processes that involve mantle rocks. This is an idea that, of course, should be tested further using other proxies of biogeochemical perturbations that we can potentially track all the way into the mantle and then into mantle-derived magmas. And with this, I thank you for your attention.
Okay, Andrea, thank you so much. Really fascinating. Let us see if we have any questions. So to remind everyone, obviously we can take questions in the room if there are, but those of you watching online, if you have any questions, you can simply raise your hand and we will see you raise your hand. Or you can simply ask a question in the Q&A chat box, which we'll see as well. So do we have any questions from the audience or from the Zoom audience? I'm going to start off then if there aren't any immediate questions. And so I'm going to take you back, Andrea, to your first part of your talk where you spoke about how we're sampling a deep mantle in these Kimballites. do you think that other magmatic products, especially around 2 billion years where you have some Kimballites with those deep signatures, do you think other ultramafic products are also sampling a deep reservoir? And I'm thinking of things that we're very familiar with, like the bushveld, still water. Are they sampling a similar mantle reservoir?
So the idea is to try to explore this question looking back at komatiites, and that's something that indeed I'm doing. The issue is that the partial melting degrees to make komatiites is so much higher than the likelihood that you also sample or oversample a lot of depleted material is pretty much certain for at least some type of komatiites, but perhaps some other komatiites, I think the aluminium depleted one, maybe might still preserve a signature of a similar source as Kimballites. This is just an hypothesis, which yet still requires to be tested. And then, of course, I mean, the idea should be also to expand to more common magma types, such as basalts, that especially those that are plume related, to see if we can see any of that.
Right. I see there are a few questions coming through. So we have one from Lou, I think. Where is that?
Yeah, I think the question was whether or not some Kimballites are derived. I think I've written it ready.
Yeah.
Whether or not any Kimballites are related to lithospheric mantle sources.
There we go.
No, I mean, I know that there are still some papers out there that push this idea, but it's just unlikely. And I think before I showed enough evidence of that, unless, of course, Louis is referring to the so-called group 2 Kimballites, which are not Kimballites, are olivine lamproites by all means, in terms of mineralogy, petrography, mineral chemistry, bullcrop geochemistry, and so on. Kimballites certainly do have a lithospheric mantle component. That's out of question. But the source is certainly deeper, I mean, before I used diamonds, evidence from diamonds, from isotope geochemistry, from trace element geochemistry, from mineral chemistry. I can also bring in some evidence from experiments, for example, things that I've been discussing with colleagues at ETH, who made clear to me that if you want to partially melt something like the lithospheric mantle, then you need temperatures that are so high that essentially you're not going to make Kimballites, but something that is way more refractory, something more like komatiites.
Okay, great. Do you have any more questions? Questions in the room? Leo, go for it.
Is it possible to say that there's a direct correlation with the presence of light on the surface of the Earth and the abundance of Kimballites that are produced? So if the intrinsic Earth wanted by itself without the occurrence of light would not have enough carbon to Kimballites and format a bomb.
So the primitive mantle which is essentially what you said before, the chondritic Earth, it does have enough carbon to make something like a Kimballite. It's just a matter of partial melting degrees. So if you have a source with say 150 ppm of carbon and you partially melt it to 0.1, 0.2%, then you can just make the math and you're going to get a lot of carbon out of it. So the concept whereby you need a geochemically enriched mantle source to make a Kimbalite doesn't really hold based on simple mass balance. Yeah.
Rachel from there, you heard it. I was curious, you showed in the Geodynamic space, you showed the Kimbalite reservoir relative to Shur and to the mantle. But then later on, you showed how Kimbalites are enriched in carbonisotopes relative to mantle because of recycling. So how could the neodymium not become more enriched than the bulk reservoirs that you were showing? Can you explain the difference between the carbon, sort of the carbon?
Yeah. So the reason why I didn't include, so the chart with neodymium didn't include the geochemically perturbed Kimbalites. Yeah, that's something that I took out for just for ease to avoid confusion. and so yeah, many of the Kimballites that have low carbon isotopic composition, they also have an enriched signature in terms of neodymium isotopes. The problem is that the correlation between carbon isotopes and neodymium isotopes is not as robust as for strontium and hafnium, because many samples come from lac de Gras, and lac de Gras has a very anomalous neodymium isotopic composition compared to its hafnium. Lac de Gras is really an anomaly and essentially screw up the entire carbon versus neodymium isotope charts. And so indeed, this is why I never show it, because it's if you take that out, yeah, there is again a correlation, but it doesn't make sense to remove lac de Gras.
But basically, then the reservoir has to stay isolated through time as we were applying to the
correct, yeah.
So it isn't really isolated domain.
It's not isolated. Yeah, no, exactly. So in the last 250 million years, we can clearly see that the domain has opened up to a lot of recycled crustal material, but only in the last 250 million years, to that extent at least. Then whether or not that domain was closed before, that's open to debate. And for example, it might be that Cullinan, just around the corner, might have seen some of this enriched material, so some subducting material already essentially affecting this domain at 1.1. Or likewise, the Finnish Kimballites at 600 million years, where there is at least one sample with low carbon isotopic composition, they also seem to show some rich signature. So I'm not sure the domain, this is my personal feeling. I'm not sure the domain was entirely closed throughout the age of the Earth, but simply the scale to which the domain gets perturbed in the last 250 million years is much higher than any potential earlier interaction with the subducting material.
And then I have a follow-up unrelated question. Like, what do you think drives eruption? So do you think it's mantle plume all the way up, and then it just becomes an eruption and then it's do you think it's actually an eruption?
No, I think of the scenarios that there were before, I think is my preferred one for most of them, not all of them. Let's make this clear, is that they are triggered by mantle plumes. These are not strong plumes, otherwise, you would have major melting events. But these are probably small filaments or smaller plumes. Things that, for example, recently I also studied some carbonatites and ultramafic lamprifiers in Angola. And also there, you don't have huge volcanism. Those are very small volcanoes, but there's a clear anomaly that is ultimately linked to the South African superplume beneath Angola. And so you don't need that much to make them, but you need something to make them. So I don't think that mantle convection can explain all of them. Maybe some of them. Lac de Gras doesn't have any evidence of plume whatsoever beneath it, but still you have 300 or more Kimballites there. So there must be another mechanism there. In that case, yeah, there might be smaller upwellings from the mantle transition zone, but ultimately you need a trigger, you need some vertical movement of material. And the evidence that we have so far shows that it's most likely that these upwellings are very deep-seated. In many cases, not always, but in many cases.
And my last question is, do you think there will be a Kimbalite eruption anytime soon, like tomorrow?
I have no clue.
Following on from that, if you had to go look for a setting where you might see a Kimberlite tomorrow, where would you go? Which place on earth would you go to?
Yeah, the so-called Clifford rule. So Kimballites only occur, well, pretty much only occur in continental shelves.
Right here.
Right here. We just need
right here. Yeah, you just need to walk around and look a little bit better and try some more.
Let's just check if there's any other questions from the audience. I don't seem to be able to see the audience very well today. I don't see any hands up from the audience. So, any other questions from the room? Okay, well, Andrea, thank you so much, especially for coming to visit us.
Pleasure.
Offering to give us a talk. And just to remind everyone that next week we'll have Judith Kinnaird speaking on critical metals and the importance of critical metals. And I think we'll continue to do it both virtually and in person, and enjoy John Hancock's kind contribution of beer. So thank you.